Today we have the eminent speaker, Dr. Harish S. Krishnamurthy, who is currently working as assistant professor in the Department of Electrical and Communication Engineering at University of Houston. So it is my privilege to introduce the honorable speaker of the program today. So Dr. Harish Krishnamurthy has done his BTech in Electrical and Electronics Engineering from NIT Tiruchirappalli and obtained his PhD in Electrical and Computer Engineering from Texas A&M University under Professor NJT, who is very popular, known in the area of isolated DC-DC converter. So currently he is an assistant professor in the Department of Electrical and Communication Engineering, Department of University of Houston. His research interests include high-density power converters and control for utility grid integration of renewable energy sources. He started his career as engineer at General Electrical Energy in power and analog electronic design at Hyderabad in the year 2008 to 10. He worked as an electrical engineer at Schallenberger REMS at Sugarland from 2015 to 2017. So he has over 5 years of industrial work experience in various reputed industries, including Ford Motor Company Research Headquarters, Google INC, Mountain View, etc. So he is a senior member of IEEE, and he is in the steering committee member of IEEE Power Electronic Society. He also active researcher, active reviewer in various reputed journals like IEEE, Elsevier, including Transaction and Power Electronics, Industrial Electronics, as industrial applications, etc. So he received an Innovation Champion Award certificate from GE for multiple invention disclosures. He has received 2 patents, 12 IEEE transactions, and 48 conference papers. So with this brief introduction, I invite Dr. Harish S. Krishnamurthy to deliver the lecture. Welcome you, sir.
Okay, thank you very much for the kind introduction. That was very elaborate, and wish you all a happy Republic Day. So I think this is a very good day to have this seminar. So let me share my screen. So it's a honor for me to present in front of you today. Basically, my topic is I think isolated DC to DC converters for electric vehicles. So basically, I wanted to give a brief of what are aspects are there in electric vehicles, and we will go to certain technical areas relevant to the DC-DC isolated DC-DC converters. So we'll be mainly focusing on the electrical charging infrastructure, because there's a lot of things like even isolated DC-DC converters in electric vehicles are used in even this 12 volt 2.53 kilowatt type of auxiliary power supplies, because now you have a lot of so many different types of electrical connections and sensors and actuators, and so many different details are in any normal cars, let alone electric vehicles, right? So these auxiliary circuits, they also need different types of DC-DC converters. The topic that we'll discuss today, they will be useful for different applications, but we'll be looking more towards more converters that are usually more popular in the EV charging. So before getting into just a quick background, so as Dr. Kumaravel mentioned, so I'm an assistant professor in the ECE department of University of Houston. So University of Houston is a large public university in Houston, Texas, and there are over 46,000 students and almost I think I would say close to 225 crore rupees of expenditure just from the College of Engineering alone per year. So So and we are significantly expanding in different domains, and even in electric vehicles we are doing considerable work nowadays with many of you know Professor Kaushik Rajshekara, who is a pioneer in the electric vehicle. So he's my colleague in the department as well. And as was kindly noted earlier, I did work in several companies, including Ford, during my industry employment before moving to academia. So at least until this time, I have actually, for my like corporate my industry experience or technical experience, I have worked more in the industry than academia at this point. Maybe in a couple of years that will change. But so usually in my presentations, I prefer incorporating aspects of the industrial designs which need to be taken care of. So some of the projects that we do are very closely developed with the industry. So we try to kind of take care of a lot of challenges which additional very typical publications alone won't capture, right? So there are very much a lot of practical challenges that we'll need to take care of whenever we do a practice, like a design practice for the industry, because power electronics is a very highly applied area. It's not a fundamental research area like maybe mathematics or some other physics domain. So we need to always have a aspect of the industry when we look forward. So please feel free to ask question or put it in the chat as explained. So let me probably turn off my video just to make sure we have enough bandwidth. So as an introduction, see, in terms of electric vehicles, we have four main types of electric vehicles. The first one, which is becoming more and more popular with enhanced battery systems, is battery electric vehicle, right? Basically, you have the main power source is batteries. Basically, you charge the batteries after a certain number of kilometers or miles, and then you use it to run electric motors. So Tesla's vehicles are all battery vehicles. Then the next class is hybrid electric vehicles. So even before battery electric vehicles became so prominent, we have been having this Toyota Prius and similar vehicles which have a typical IC engine as well, but then you also have an electric motor. So the main purpose, along with batteries, maybe a much smaller battery system. So the main purpose of the battery is, especially when you're braking or decelerating, your energy from the wheels and other systems can actually flow back to the battery. So basically for regenerative braking purposes, and also maybe for very short distances or maybe very low speeds, maybe you don't really have to use the engine. So predominant part of the energy comes from the batteries. So what is the advantage there? Typical mechanical systems in in non-electric vehicles, right? Traditional vehicles, they may have anywhere from 60 to 70% efficiency. I mean, 70 is like still very high, but once you start having these electric motors and batteries and so forth, your system efficiency can go beyond 90% very easily. So so especially with so many different vehicles coming together, it actually provides a lot of benefit moving to electric vehicle. So of course, traditional battery electric vehicles will need so much of battery systems. So again, disposing the batteries, those are again bigger challenges. But hybrid electric vehicles, the battery system is much smaller. Now, plug-in. So, by the way, like hybrid electric vehicles usually do not need a charger, right? Because the battery just gets kind of refilled from the motor or generator itself. So, plug-in hybrid vehicle is more like a mix of the top two. So you have battery systems which can be charged independently. At the same time, you also have engine and gas tank and petrol tank and so forth, right? So that's a plug-in hybrid electric vehicle. Then another class is fuel cell electric vehicles. So these use hydrogen tank and which can be fed to a fuel cell, which generates electricity. You also have batteries, and which drives the electric motor. So fuel cells are pretty good. The only problem is, they may be a little more expensive, and considering battery electric vehicles are becoming more popular, so that's that's a debate on which part we need to go. So people from the fuel cell area, they say that battery electric vehicles use up a lot of lithium-ion batteries, and you need to dispose them in the future, so it can cause issues. At the same time, like fuel cell, as I mentioned, they are pretty expensive. Now moving to the charging infrastructure. Basically, we have AC level 1, level 2, and DC fast charging, and so forth, right? So basically, level 1 charges close less than 2 kilowatts. That's pretty common. Even our residential household systems can handle that. And AC level 2, we need in the US it's 208 or 240 volt single phase AC, and those charging loads can go up to 20 kilowatts. So what that does is that can charge maybe 10 times faster than the typical AC level 1 charger. So level 1 charger probably it may very well take 10 to 12 hours for fully charging the car. So that can be a problem, right? So now modern researchers have done immense amount of work on DC fast charging. So of course there is AC interconnected fast charging and also the DC fast charging. So depending on what you feed into the car. So well over 100 kilowatts have been demonstrated. Even wireless charging over 100 kilowatts have been demonstrated here in Oak Ridge National Lab in the US, and it's a very interesting time for fast charging. So companies like Tesla, they are also trying to get this charge done in 20 minutes or even less. Now, when we talk about charging, there are several important aspects to it, right? Like, especially so, ultimately, from the grid, we need first we'll have this filter. We'll talk about why that is needed. But then basically you have AC to DC rectifier stage, and then that's connected to a power factor correction stage. In some topologies, these two, rectifier and power factor correction, can be combined together. So if you use converters like VNR rectifier or PWM rectifier and things like that, so there these two are technically kind of combined into one, right? So here instead of a diode rectifier and let's say a boost converter followed, you can actually combine them to one, and then followed by a DC-DC converter, which is usually isolated for several reasons. We'll discuss that, and then that goes into the battery for EVs. So then there are two types of concepts, right? Like one is onboard charger, and then off-board charging. So for onboard chargers, of course, they are going to be inside the car. So you need to make the entire system as small as possible, as efficient as possible, and as inexpensive as possible, right? Because you don't want to create a lot of heat. And if the size is too large, you'll have to fit in along with all these battery banks, which themselves are very large. And then safety is a prime responsibility, right? Like basically you're connecting the when you're charging, and the battery voltage and all put together, you need to make sure that there is sufficient isolation. Especially, let's say it's very much possible that when you're charging at your home, maybe your kid can probably get into the car, and it should not affect such scenarios. That's the reason why you need isolation at some stage, and it's preferable that it's in the DC-DC converter stage, which is the main topic of today's lecture. Now, this is a little bit elaborate. We'll, as we discussed, we have a rectifier here, then boost PFC. So the main purpose of this PFC, I'm not sure if you had a different session to focus on these domains, but the power factor correction, it's the most common. This particular topology is one of the most common topologies found even in cars such as in Tesla. So they do have a boost PFC stage where the current through this inductor is tried to be made similar in shape compared to the voltage that appears here, eventually translating to the current here being in phase and very similar in shape that of the voltage. The EMI filter in such a scenario will probably be designed for the switching frequency of this switch. So you need to like probably clear out maybe some 100 kilohertz frequency or anywhere around that. So that's where this EMI filter comes in. So if you didn't have this boost PFC stage, this rectifier would have created third harmonic and other unwanted harmonics. Then it would be a big challenge. So for off-board systems, maybe such an approach is okay, but now with availability of very advanced converters and also even PFC, such a aspect is not even discussed. So once we start going to very high power, as I mentioned, you start combining these two to something like a VNR rectifier or a PWM rectifier. So then again, the EMI filter has to be designed for a very high frequency. Now it's the part which we are waiting to kind of discuss today. That's the isolated DC-DC converter stage. Now there are multiple reasons why one would use an isolation. As I mentioned, the safety is of paramount importance. Like when we are charging, especially this input voltage is usually connected to the ground, and then you want to make sure that most of the this particular portion is limited to a very small space, and there is sufficient insulation. So whatever is coming out on the other side, it doesn't cause any shock. So that's very important. Then this particular converter has to also step down or step up with regard to how much is the battery voltage. But at the same time, in very practical applications especially with lithium-ion batteries, there are different charging modes for this converter, where we'll discuss that in one of the slides. So there have been, as I mentioned, especially when you consider off-board charging, where your battery connection is directly available from the cars. You can actually use solar PV panels or some other sources to actually combine with traditional grid to charge the batteries. But this is usually because with PV panels, it's not possible to be onboard charger. So this is something which people have been using in some of the charging stations which are off-board charging. So that's indeed a interesting prospect. So PV panels will offset some, because especially once we start looking at hundreds of cars, or at least tens of cars in one location, and then you are charging with 100 kilowatts, it's a very high power for a very short time. So there are a lot of challenges coming onto the grid side. Again, that's something which many are looking into. And on the onboard charging itself, as we discussed, this is a very typical structure that is drawn on the left. But on the right, actually, some of these converters, you have a DC-DC converter on this part, and there's another DC-DC converter on the other side of the battery, which kind of goes to the motor. So some researchers have found a way to use the DC-DC converter for bidirectional charging and use the grid connection. So basically, during the charging time, you don't use the motor, right? Because during charging, you are not running the car. So using the generator itself with a relay, you can use that as an inductor and use the inverter as the PWM rectifier, which I talked about a little while before. Then you can actually charge the batteries. And then when you are not charging, you take this relay off. Basically, then you literally operate these as motors. So this is an interesting concept, which some of the researchers are still looking at, and looking at the potential to probably reduce the overall size of the EV system. Now, with the isolation, one obvious way of doing it is wireless charging. And I think 2007, there was a paper from MIT which demonstrated you can actually do several meters, power transfer under several meters. And this has been taken to a very, very far distance by several folks in industry as well as academia worldwide. And as I mentioned, more than 90 or 100 kilowatts wireless charging at 97+% efficiency have been demonstrated. It's a very, very high bar which have been set in practical scenarios, and several companies are actively pursuing this research. So of course, wireless charging technique, depending on you can either make it as an inductive charging, is basically like a transformer, but then you need proper alignment between the primary and secondary coils. Then there is a magnetic resonance charging, which is not that suitable for electric vehicles because these are more or less for relatively lower power. But wireless charging is really making a big stride in the industry. Now, we also discussed a little bit about um, uh, lithium-ion batteries and what this isolated DC-DC converter needs to do. So, as such, we cannot so a battery, when delivering power, can actually supply the required load power, right? Like typical sedan cars, you will probably need close to about 140, 150 kilowatts, and that actually goes higher with a larger car. Maybe a 7-seater vehicle, it could be like 250 kilowatts or so, right? And with this 150 kilowatt, you need to that much of power has to come from the battery. So batteries can deliver a lot of current at the same time, but traditionally for the life standpoint, you would want to maintain a charge rate of 1C as per the rating of the battery system, because otherwise it is possible that we may overheat the batteries, and so the charging is a little bit more delicate. So this is a very typical capacity versus time for charging lithium-ion batteries. Of course, this time is probably too short for EVs, but this is just how the battery charging works. So usually what we do is, when the battery voltage is low, like as you see here in the red, um, uh, you apply constant current charging. So charge current again 100% as corresponding to charge rate of 1C, and so for some time you kind of pass constant current, and this black dotted line shows the charge capacity. So at some point, the terminal voltage will almost reach the peak. It won't be exactly the peak, but let's say the battery voltage will almost reach its designed peak, but you still have a long way to go in terms of the total charge capacity. So once the voltage is at its peak, you wouldn't want to do a constant current charging. The main problem is you keep on doing that, and you won't have too much control on how the voltage rises. So at this point, you do something called a constant voltage charging. So you adjust the charge current in such a way. It's usually in this exponential type of curve, or exponential decay type of curve, where the voltage is fairly constant. And at some point, once everything is, once the batteries are fully charged, usually the current actually comes down close to zero. And every now and then, if you want to still charge them more, you can do apply a few bursts of current. So this is a very typical charge profile, whether it is a cell phone charger, or whether it is a electric vehicle charger, and so forth, right? So this has to be replicated by the isolated DC-DC converter. So that's a very important factor. Now let's go into some of the basics of isolated DC-DC converter. So there are a lot of DC-DC converters, like buck boost, and I'm sure you all know about that. So the isolated DC-DC converters have several advantages, and of course there are several disadvantages as well. Like when I was at Ford, I remember my manager saying, if there is a way to safely employ a non-isolated DC-DC converter in place of an isolated DC-DC converter for electric charging, we would be very happy, because the isolated DC-DC converters can be larger and also can be more lossy compared to a non-isolated DC-DC. Then said, the only other options for the safety purposes, where whatever you have galvanic isolation, only other options are probably a switch capacitor coupled DC-DC converters, but those again, their relevance for such high power is questionable. So at least at this time, we still have to live with isolated DC-DC. But again, with the advent of wide bandgap semiconductor devices like silicon carbide and gallium nitride, already these things are becoming very, very small with even with isolation transformer. So what all benefits do the isolation transformers bring? So they provide step up, step down, which will match what is needed for the battery side from whatever is the grid voltage. Then you have you can actually get direct current power isolation. Then these prevent the risk of electrical shock. That's the main idea for using these. And another main important aspect is you can decouple the noise, especially in many applications, the transformer core, there's usually a copper shield, and then the copper shield can be tied to the ground. And that actually again decouples the noise moving from the input side to the output side, as well as the output side to the input side. Remember, a modern electric vehicle chargings, they require different types of communication along with the power. So you would want to keep the noise to a bare minimum. So that's an extremely important aspect. So the transformers have such benefits. Again, because they are onboard chargers, we are doing away with the traditional low frequency charging, low frequency transformers. So we want to take these transformers to several hundreds of kilohertz, if not megahertz. So we want to take this transformer core material, ferrite core, nanocrystalline core. They are pretty much very much tuned and optimized for anywhere from 300 to 400 kilohertz. So so long as we use gallium nitride and silicon carbide FETs, we can actually operate such converters at that frequency with significantly above 98% efficiency for the isolated DC-DC, which is a big achievement, and people are already doing that. Now let's look into the transformer a little bit more in detail. So are there any questions? Should we stop or just continue? Hello?
Yeah, I think we can continue. We can continue.
Okay, so we'll finish everything and then take questions.
Yeah, yeah.
Okay, yeah, okay. So transformer model, so transformers are very interesting, right? Basically, it's we somehow take it to a simplified structure and assume that everything will work fine. But there are a lot of things going behind, right? So usually when we talk about a transformer design, many people would just say, oh, so long as I find out what is the turns ratio required, and I put it in some simulations, and or maybe just get some off-the-shelf transformers, and we are done. But transformer design is a lot more, right? So you have to look into the core losses, the winding losses, proximity effects, then saturation, efficiencies, and leakage, and so there is so much going on. And every single aspect of this transformer here has to be taken care of to design a good converter. So when you look at the model, basically, of course, you have the magnetizing inductance, which is a fictitious inductance, which you would assume ideally to be infinity, because the larger the magnetizing inductance, your magnetizing current is smaller and smaller. But the problem is that this inductance has to be defined by the number of turns. If you want infinite inductance, you technically have to have infinite number of windings, or get a core material that is unimaginably good. So that is practically not possible. So we have to live with the required size. So there's a lot that goes on with optimizing this magnetizing inductance. Now the leakage inductance, there is the opposite. We try to usually keep that to a bare minimum for some reasons. Of course, in some applications, we would want that to be large. We will discuss basically on, especially when we talk about soft switching and some of the resonant converters, we may look at the leakage inductance. We would want it to be a little higher. Then said, if they are a little higher, there are some other challenges which come in. So again, there is an optimization which are governed. Of course, I'm not showing the core loss model here, but yeah, it's shown in the bottom figure. So basically, the RC will define, and that's itself is a nonlinear function with frequency and flux density. So basically, like that defines what would be your loss at different frequencies and so forth. So ultimately, there's a lot to look into. So now, just take a hypothetical situation, which again is important for the rest of the talk. Is, let's say if you have a positive voltage applied, right? So when you have a positive voltage applied here, I think I should be able to annotate. So if there is a positive voltage applied here, then I hope you can see the paint. So what happens is, of course, if we conveniently disregard this, it would just seem as though the entire voltage applies goes to the load, and with the transformer turns, your output voltage will be like just V in multiplied by NS over NP or something like that. But what happens is you also have this XM and RC. So what this magnetizing reactance does is, whenever you have a positive voltage, the magnetizing current IM starts increasing like this. And then when the voltage becomes negative, it actually starts going down. So one aspect for avoiding the saturation effect is that the average value of the magnetizing current, you would want to keep it to 0. But when you think about it, the primary current maybe changing like this, going up and down, but you have to add this particular signal which actually goes up like that. So there is some additional current which the magnetizing inductance itself causes. So we will discuss that a little bit more in coming slides. But with purely the transformer diagram, you have to note that these magnetizing inductance and the remaining aspects of a transformer, they play a big role in defining how the entire converter works. So now let's look at a little bit more about what are the overall different types of isolated converters. So you can define isolated converters and under two main categories. One is a single-ended converter. Some examples are forward converter and flyback converter that you see below. And then double-ended converter. So on this slide, we are mainly looking at single-ended converters. So what that does is, if you think about how a forward converter works, so basically when the switch turns on, there's a voltage applied across the primary of this transformer, and then when the switch is turned off, there's a reset, there's a reset winding and so forth. But ultimately, there's a net average voltage applied on the primary side. So when from a transformer's perspective, the flux BH curve usually stays on the first quadrant, right? So we are not utilizing the third quadrant of the transformer's BH curve. So basically, because of this underutilization of the transformer, number one, the transformer for these applications actually are usually larger. Number two, we cannot use these topologies for very high power, maybe up to a kilowatt. If you design them very well, they are okay. But once you start going beyond that, single-ended transformer-based converters are not that suitable. So that's a big challenge. Like flyback converters or forward converters are very amazing for like 500 watts and less. But once you start looking at more than a kilowatt, like especially for the EV charging, then that takes a big hit in terms of efficiency and size and things like that. Now, so gapped flyback transformer. So as most of you know, the flyback converter's transformer needs an air gap, because unlike a forward converter, the flyback converter, when the switch is on, there is no current flowing to the secondary. basically when the switch is off, the energy stored in the air gap. That's the reason why you need an air gap in the flyback transformer. I mean, basically it can be considered a coupled inductor, not necessarily a transformer. So the energy stored in the air gap actually flows to the load when the primary side switch is off. Now, once you insert this air gap in the transformer, there are several things that happen. One, the effective permeability is now dominated by the air gap. So effectively, your mu permeability or relative permeability mu r, that actually drops. So you see this blue trace. So that's the blue trace is a little less steep than the black trace. So what that does is that you're for the increase in current, your flux doesn't increase as fast. The good thing is it will reduce the saturation effects even for a higher magnetizing current. But the bad thing is, again, like, you will need more number of turns on the transformer in order to achieve very similar performance. So basically, like, that's one of the reasons why flyback converters, transformer or coupled inductor, it needs to be large. And another thing is, of course, like, in terms of saturation, it has some benefits, and that's again, like, a very useful aspect when we design DC-DC converters. Now, moving on to double-ended converter topologies, you see here, like, it uses both first quadrant and third quadrant very effectively. Of course, there is a very tiny portion, of course, and also we want to reduce this tiny portion on the second and fourth quadrants to a bare minimum. But there is still a very tiny portion because of the residual magnetic flux. And if you note here, the area under the curve of utilization, that actually constitutes the losses in the system. So in double-ended, at least the benefit is we are utilizing both quadrants of the BH curve, like number 1 and 3. So naturally, this provides a lot of benefits. It improves the power density. It actually calls for like usage for very high power. So applications involving hundreds of kilowatts can be realized with such transformers. Because there is something called an active clamp forward, which is a part of single-ended. So basically, it's a part of a forward converter. So, but the mode of operation has a very tiny current flowing in the reverse direction. So there is a very tiny portion of this active clamp forward, which can be considered double-ended, but that's because of the clamp and not necessarily because of the forward. Now, once we start looking at half bridge and full bridge converters, again, we'll look at the topologies in a bit. If this is the voltage at the primary of the transformer, sorry, this is the current going through the primary of the transformer. If the current looks like this, it's pretty normal. If it looks like this, it means there is a flux imbalance, though it is not saturating, because this is still very linear. So which means that in one set of switches is operating slightly differently compared to the other set of switches. Now, then the next situation which comes in after this is where, let's say there's a massive flux imbalance that actually drives the transformer to saturation. So when the transformer is saturated, which means you're like, trying to go in this shaded loop, and then suddenly, like, the current is high, magnetizing current is high. So you tend to go up here, and what happens is that your current, magnetizing current is so high that your B it kind of gets saturated. So the flux gets saturated here. So what happens is the permeability is given by the change in B over the change in H. So in this region, that makes the relative permeability very tiny. So when the relative permeability is low, as you may remember from like further classes, inductance is proportional to the relative permeability. So basically that reduces the magnetizing inductance, and when the magnetizing inductance is smaller, it literally, like, that in the smaller inductance in this region makes the current go much higher because V equals L di over dt. And when your L is low, your di, the changing current, actually becomes more. So if you find, if you are doing a isolated DC-DC converter, and if your current shape has non-linearity like this, you are doing something wrong. So that's an aspect that you should always look for. Now, moving on to the converter topologies by themselves, you know, this is a very simple H bridge, which is very prominently used. So basically, you have 4 switches. It could be any switch like silicon or silicon carbide or gallium nitride or any of these switches. So here it just shows a typical resistive load, and it's almost always not a resistive load. Like in practical scenarios, you never have a resistive load, right? Basically, when you think about an electric vehicle, you have a input. Again, it's an AC system, but then again, after the rectifier, it's a DC, and then the battery is also DC. So imagine you have 2 DC sources. You have to transfer power between 2 DC sources. So that's a much higher challenge than purely modeling something as a resistor. So again, if you're working in the areas of electric vehicles and battery charging, I would suggest model the system properly, not use the resistive load, like not use pure resistors as your load. Now, so let's say how this works is when T1 and T2 are on, basically these 2 switches are on, the DC voltage is applied like positive on the left across this resistor, and then when S3 and S4 are on, then basically a negative voltage is applied across this resistor. So basically you see, like when you look at these 2 modes, you combine them and you get a square wave type of thing, right? Basically it goes up and down. And there are 2 other modes. One is basically S1 and S3 turning on and the other 2 turning off. What that does is that makes the voltage across the load in an isolated DC-DC, that becomes the primary of the transformer. So the voltage across the primary of the transformer now becomes 0, not positive, not negative, but 0, right? So that creates 0 states. That's very heavily used for different operational scenarios. You can also create 0 states by turning on S4 and S2 at the same time. So basically the voltage across, let's say in this case a resistor, if S4 and S2 are turned on, then your voltage applied is actually 0. Now, this is a very, very common isolated DC-DC converter stage with a full bridge on the primary side. Again, it's very similar to what we saw in the previous page. The only addition is you have this body diode for the FET, which comes into picture. And this models the magnetizing inductance of the transformer. Just to note that when we apply a voltage, it's not just the load current, but it also includes the magnetizing current that needs to flow through each of these FETs. Now, on the secondary, I'm showing a push-pull configuration. So with the push-pull configuration, one challenge is your voltage across the diode it needs to be twice that of the output voltage similar to that rating, because basically when one of these diodes conducts, the voltage across the other diode is twice the n times V in. So basically each of these winding will be n turns ratio times the voltage appearing here. But then this diode has to look at twice that voltage. So that's one of the challenges. But considering this has very few number of components, this is a very highly used topology on the secondary side. Now we can also have other ways of doing it. Like basically, if you look at this, you have a full bridge on the secondary side as well, very much possible. And you can also use FETs instead of diodes, because like especially with MOSFETs or gallium nitride FETs, you can operate those devices also as synchronous rectification mode. Now, there is also something called a current doubler scheme. It's not that common for certain reasons, but then these topologies have also been used in some cases. So we just have a single instead of a center tap, you kind of create a center tap using diodes or FETs like this. And what this does is it creates a current doubling mechanism that so basically you can achieve twice the current using this topology. But again, like I said, I don't want to go too much into this because this is not that common. Now, how does this converter work? So that's something which we need to like really look into. So basically, this particular converter, you have when you have like T1 and T4 on, as we discussed before, this transformer magnetizing current will increase. So the voltage across this seems like whatever is input voltage that appears here, and now this I of t, so that is in fact so the IT will also have a ripple which is governed by the magnetizing inductance current. So on so this is Vs. I'm sorry, I think some of the voltages have not been listed here, but anyway, I'll try to explain with that. So the secondary side voltage is actually it will be n times that of the input primary side voltage. So but one thing you notice is that whenever on the primary side, if we have a certain switching frequency, the voltage on the secondary side will actually have twice the switching frequency, because the rectifier on the secondary side will actually flip the voltage appearing at this region. So that's the reason why we have 2 times N2 over N1D, considering the duty cycle is the duty cycle of each FET on the primary side. So let's say if you want 40% duty cycle, so T1 and T4 are on for 40% duty cycle, then T1 and T4 become off, let's say in this region, so there is no voltage applied, and after that T3 and T2 are on, so that we create a negative VG voltage, and again after that we turn it off for some time. So depending on the duty cycle, your output voltage can be found out using this equation given here. And this diagram actually shows the different types of like different devices that are on at the same time. So one thing again to note is like when two of the switches are let's say instead of T1 and T4, when we are like creating a zero state for the primary voltage, what happens on the secondary side is this inductor still carries a current forward. So this current, especially when the input side is input voltage is 0, this current actually now splits one half flowing through diode D1, another half flowing through diode D2, and those two flowing through the transformer secondary windings get cancelled out in the magnetic field. So that's how, even without the input voltage being applied, these two currents can balance out. So that's why you see that on the, so again, sorry for the denomination. So this ID5 has to be in fact D1. So basically this D1, you see in this mode, it's half of the load current. So here I is in fact I0. So this is a very typical flow of current for isolated DC-DC converter. Now, so this up to this point is more of the fundamentals of isolated DC-DC, and from here we are moving towards phase shifted full bridge. So as we discussed, our primary so probably we can take it here. So our primary side FETs, like multiple ways of operating them are, you can turn these two on for some time, turn them off, and then turn Q3 and Q2 for some time and turn them off. So that's very, very straightforward. But in a practical design with controllers, that's actually a little bit more complicated to do. It's usually easier to generate 50% duty cycle. So the alternate way is to actually have Q1 and Q2 both having 50% duty cycle, and both being applied, Q1 and Q2 are complementary to each other. So that is one way. And on the Q3 and Q4, they are also something very similar. Like Q4 is complementary to Q3, and both of them will have 50% duty cycle. The only difference being, instead of 180 degrees phase shifted between these two legs, we would add some additional phase shift. So depending on how much more, so if you do not add a phase shift, the almost the complete voltage will flow through the secondary. The more phase shift you add, what will happen is there will be more zero states created here. So I can annotate here, so just to show the difference. So basically, so this color is, so let me take a red color. So imagine, oops, what is that? Okay. So let's say you have this waveform, and you create a phase shift. So if you look at the pure subtraction of these two waveforms, you can see that at this point there will be sorry for that. At this point there will be a positive. So I think. So there will be a positive voltage, and then the difference becomes 0, and then there will be a negative voltage, and then the difference between these two signals becomes 0. So the more we increase this phase shift, we can actually adjust the duty cycle of the resulting voltage, which goes into the primary of the transformer. So this particular mode of operation of this converter is called a phase shifted full bridge. So in terms of the phase shifted full bridge itself, there's another way of operating is, basically you phase shift between the primary side and the secondary side. Now, with the, DC-DC converters, there are multiple ways of deciding whether are you going towards, zero voltage switching or a zero current switching and so forth. So imagine that you have a, LC resonant LC series connection in front of the transformer. So the LC and the remaining network here will have a resonant frequency, which can be termed as FR. Now, if your switching frequency is lower than the resonant frequency, what will happen is that the L omega term will actually be lower than the 1 over C omega term. So that will actually lead to a current leading effect. That's what you see here, right? The current leads. The current here actually leads the voltage by a certain amount. So what this does is that you will find the way that this converter works. This switch Q1 and Q4, they turn off when the D1 is in conduction. So basically, when the diode D1 is conducting during this region, if you notice here, then the switch Q1 is turned off. So what that does is it creates a zero current switching phenomenon at this point. So the loss of this the losses in that switch will actually be very low. Now, if we operate below resonance, like when Q1 turns on while D2 is conducting, the stored charge of in the D2 and of the semiconductor output capacitances must be removed. So that's one of the challenges that you will see, because otherwise you may end up seeing these type of spikes in this type of a switching scheme. Now, zero voltage switching is actually preferred more in such a scenario compared to zero current switching. So there are some reasons why it is so. So if you look at the conduction sequence of zero voltage switching, zero voltage switching can be obtained when your switching frequency is actually higher than that of the resonant frequency. When that happens, the L omega term is actually higher than that of the 1 over C omega term. So basically your current will lag the voltage at the resonance, and what that does is when the Q1 switch is turned off at this place, right? So when the Q1 switch is automatically turned off, and this voltage actually goes negative, so the D1 diode will turn on. So the Q1 switch turns off when this diode is conducting, and that causes a zero voltage switching. So with above resonance, you can actually get zero voltage switching. But we may think there is a problem for turn off transition for this type of at above resonance condition. So for turn off, basically Q1 turns off, the D2 must begin conducting, but it may look like it is actually not turning off at the right time. So we may think that this is hard switching because the current is still high. But there is one more mode of operation for such a situation where, so this is this is not just for resonant converters, but even for regular whether you're using it with phase shifted full bridge and so forth. This particular mode of operation is always there. So all the four devices in the full bridge actually have parasitic capacitances across. Now, once you operate with Q1 and Q4, the leading diagonal, and if you turn off Q1 and Q4 for a brief period and do not turn on the next set of switches, so there is a commutation period here. So since there is some current which is already flowing through the primary of the transformer, because you have some inductances connected there, so there will be some flow of current. So that flow of current, irrespective of whether these switches are turned off during that time, that will actually draw the charge from one capacitor and then recharge the other. So if you give sufficient time between the transition, the capacitors across the switches will automatically provide a zero voltage switching transition. So it's just to kind of highlight the aspects for zero voltage switching, especially with full bridge. Actually, it can provide a soft switching for both turn on and turn off. So that's something to keep in mind. So of course, if you follow the book by Professor Erickson, actually there are many more details which actually you can find out and read. Now, like further going into phase shifted full bridge. So as we mentioned, phase shifted, we already talked about the primary side of the full bridge converter. Now, in terms of the phase shifted full bridge, there is another aspect that we need to look at from the secondary side. So how do we so if we simply use diodes as we showed in the previous situation, it will work quite fine, not a problem. But the only difficulty is once we start going at higher loads, they may cause more losses because the diodes are very lossy, right? Compared to a typical silicon or gallium nitride MOSFET, a diode has a much larger on-state drop and they can be lossy. So I'm assuming like you all know about the synchronous rectification, which are used in buck converters and boost converters often. So these similar modes can be used on the secondary side, where you can actually put switches instead of typical diodes, and there are different modes of operation here. Like mode 0 is when you simply use them as diodes, basically like, do not gate them, and then they just simply operate as diodes because of the body diode in a typical silicon FET. So, but then whenever your load conditions change, whenever you have a heavy load, then you can actually activate these switches so that your on-state drop is significantly lower. So, so this particular design is called synchronous rectification with phase shift at full bridge, and this can be very handy to achieve soft switching as well as low losses in phase shift at full bridge. So as I mentioned, the theory of operation is very similar, but it's just how you control the secondary sides using the different mechanisms available. We can either put them in mode 0, 1, or 2, depending on what load condition the particular converter is. So I don't want to go too much in detail on this one because we already discussed about it. Basically, as you see here, whenever there's a 0 voltage appearing on the front side, the voltage, the primary is 0, so the net voltage on the secondary has to be 0. So the current actually bifurcates through these two diode paths, and then the voltage kind of gets compensated. So there's no flux imbalance. So we already discussed about the waveforms earlier. Now, some of the practical challenges that you would find with phase shifted full bridge. So as we saw, basically we want to, the maximum voltage which we can achieve is based on, let's say we apply close to 50% duty cycle for the leading diagonal as well as the other diagonal, right? So basically we are making the phase shift close to 0. But there is a challenge. So especially when you have a lot of these parasitic inductances and even resistors in the system, these inductors actually do not let the current to rise very fast or fall very fast. So there is always going to be a finite time, especially during the dead time, as we see here. So during the dead time, there is always a finite time after which you are the voltage which you apply here to translate to the output capacitor, it takes some finite time. So as you see here, basically there it takes some time, and what that does is on an average you have a little bit loss of the effective duty cycle. So our equation may say 2 times d times n times v in, but practically we won't achieve that. So this equation actually provides for a certain design, like especially when you are very tight in terms of the design, you have to design the transformers with such different such a scheme to make sure that you don't have a lot of duty loss. So that's something which you have to note. And some of the projects, maybe one of the projects that we are doing now, we face such an issue at the beginning, and we updated the leakage inductance design accordingly. So another aspect, as we discussed before, is the transformer saturation effect. So basically, when you have like, let's say there are switches and all 4 switches need not be of the same type. So we would assume that the voltage at the primary of the transformer is so symmetrical, but in reality there may be slightly more losses on the other 2 MOSFETs, and which will create an imbalance which is shown in red. So what this does is, over a period of time, there will be more positive voltage, net positive voltage applied, which actually, so imagine, like, when you apply a positive DC voltage, a net DC voltage across an inductance, the current through the inductance rises without any control, isn't it? Basically, you're applying literally a DC voltage, and then across an inductor, the current just goes up and up without any control. So at some point, it will get saturated and damage the FET. So one way to eliminate that problem is by placing a large enough capacitor in series with the LC. So when we have an LC, it doesn't always behave as an LC resonance system. So if the capacitor is large enough, then it behaves like a traditional phase shifted full bridge, but the capacitor does block the DC so that the transformer doesn't saturate. So this is a very common practical design. And another benefit of this capacitor is, even though we have this capacitor, the voltage blocked by this capacitor is very small. So this particular work was done by my student. Basically, he was trying to assess like different values of this capacitor. So if we like with DC capacitor, DC and low frequency components can get eliminated. So small, if we reduce the value of the capacitance, it actually provides a better attenuation for the DC components. So as you see, like this is a 400 nanofarad capacitance for a certain design, and then this is blue is a 2 microfarad capacitance. So with the 400 nanofarad capacitance, your like attenuation is minus 100 dB. So that is good. But a challenge with smaller and smaller values of CR is that in the response of the voltage, you see more ringing. So we need to arrive at a balance. So maybe the blue trace probably is better than either green or red. So that's a design challenge that you will have to stick with. Some other challenges again with such topologies is basically, you have this leakage inductance. On the secondary, we have these parasitic capacitances across the FET or the diodes. This leakage inductance and then the capacitance actually start resonating, and across the output voltage, secondary, you will start seeing waveforms like this. So this was seen in one of our designs when we didn't have the compensation circuit, which I'll show in a minute. So you see how much terrible ringing is occurring on the voltage. So again, this is mainly because of the coupling between this leakage inductance and then the capacitance. So there are multiple ways of solving. One is by adding clamp diodes on the primary side. So and secondary thing is you can add RCD clamp on the secondary side. So but if you just have a diode clamp, of course, your system compared to what you see here without clamp, your system is much better. So at least the ringing is ending after just a few cycles, but still probably is not good enough. So with the RCD clamp, you can see that the overshoot has been tremendously reduced, and a combination of these two, it's much better. So, but the problem with the RCD clamp is it is lossy. So you have to strike a balance between the efficiency of the system and how much ringing can you tolerate. So if you can tolerate higher ringing, like if you have enough capacitances on the secondary side, then you may be okay. So all these pretty much you may very well face in an EV charging application. Now let's quickly go. I think there's probably not too much of time, so let's quickly go into some aspects of resonant converter design. So starting with a simple series resonance switch. So you'll find that when you have a simple series resonant circuit and then an equivalent load denoted by 8 over pi square times R, assuming it's a rectified load, right? Like on the secondary side of an EV charging system. So we can actually look into what is going to be the effective impedance in front and understand how the system behaves. So you will find that the input impedance has a characteristic something like this. So what this does is, it's more like a band reject filter type of scenario, right? So basically, at certain frequency, the net input impedance is low. So and depending on how much the value of Q is, we can actually make this either narrow or wide for different applications that we are looking at. And LLC resonant converters actually add one more inductor. So basically, we are considering the magnetizing inductance of the transformer also. So in most cases, a traditional LC resonant converter is most likely an LLC because the transformer magnetizing inductance is also there. So depending on the scenario of the effective load being very high or the effective load being very low, your inductance. So for a large load, this magnetizing inductance is almost invisible to the input. But then when your load is like when RAC is infinity, then basically it means that the load is very high. So in such scenarios, your inductance will come into picture because the effective parallel combination LM will dominate. So what that does, it will provide a sufficiently higher current to achieve soft switching with LLC resonant converters. So LLC resonant converters are some of the most commonly used isolated DC-DC converter stages at this time. So again, the design of this LLC resonant converters can be very challenging. The gain equation. So for LLC resonant converters, you know, you don't always get to change the duty cycle because you won't get soft switching properly. So the way that people try to achieve soft switching is by controlling the frequency of the operation. So of course, if this transformer is designed for 500 kilohertz, we cannot go for, let's say, 200 kilohertz or 800 kilohertz, because then it will not be optimized. But so long as we vary within, let's say, 450 kilohertz and 600 kilohertz or something like that, your transformer will still operate well. At the same time, your soft switching performance will also be pretty good. So the depending on how well you can tune your LLC network, you can actually come up with different gain eventually, which will denote how much output voltage you will achieve using the LLC resonant converter. So this operates slightly different compared to phase shifted full bridge. The phase shifted full bridge, as I mentioned, when you change the phase shift, your output voltage also changes. But here you can change the frequency. So so basically, this we can come up with a constant, which is a ratio of the magnetizing inductance to the leakage inductance. So one thing to remember here is usually magnetizing inductance is supposed to be much higher than LR. So the K value naturally becomes high. But when you look at these functions and start looking at what you would need to have to achieve a pretty good design, you need very sharp transfer function for this particular system. So that will actually, with that, you can achieve very rapid gain. So this actually it impacts the gain of the converter. So if you slightly change the frequency, the gain tremendously changes when you have a high Q. But then if you have a very low value of Q or a high value of K, then even if you change the frequency a lot, your gain is not changing much in these regions. So you would prefer having a high Q and a low K value. But as we discussed a little while before, if having a low K value, it needs the a higher leakage inductance value, which is LR, or the series inductance. So in a practical design, we will have to add a lot more inductance. But as we discussed in some of the previous slides, that can also cause duty loss, and effective power transfer may also get affected. So there is again a lot of trade-off. You can actually read more in this paper that we had recently published, because this is a very important aspect when you look at LLC converter design. So we'll quickly touch upon one final aspect of isolated DC-DC converters. So far we have been discussing about this topology where you have a diode rectifier, or any rectifier followed by an isolated DC-DC. So one of the work that I did a little while before is, instead of this is especially better if you use a three-phase system. So if you have if you can combine these two stages to a single converter, that can significantly reduce the size and reduce the heat. But again, so we went with a matrix converter. So I think many of you would have heard about that. It's a AC to AC converter using bidirectional switches. So this particular matrix converter does two things. One, it will make the input current quality high, and at the same time, it will make the transformer operating frequency also close to where it should be. So basically, let's say if it is 100 kilohertz, the output AC effective voltage will be 100 kilohertz. At the same time, the input current quality will also be good. So the modes of switching of this particular converter have to be split between an input PWM current based current source based operation, and then an output a square wave inverter based operation. So both merged into one single matrix converter. So with this, we can achieve like a single stage conversion. So there were some questions on why would you use such a topology? So I agree that when we have a traditional topology, especially with three phase, we may not necessarily need to go for a matrix converter, but with modern gallium nitride devices, some of them can actually operate in 4 quadrants. So these two switch can be combined together to one gallium nitride switch. So it can significantly improve the efficiency and also reduce the component count. So I'm looking at, I'm trying to work with some companies here on gallium nitride to come up with such an architecture where you just use one GaN FET instead of this anti-series IGBTs or MOSFETs. And again, I don't want to go too much in depth on the matrix converter switching. So basically, this switch again, it shows the current performance on the input side. Basically, if we generate a PWM, which is synonymous with an AC waveform, then your input current quality can be made high. But at the same time, that's actually multiplied with the switching function of a square wave. So the output voltage of the matrix converter is a square wave of voltage. At the same time, the input is of good quality. So this shows how the converter can be operated. So we can use this, employ this as a phase shifted full bridge by creating a phase shift between the primary and secondary. The only difference is the primary, because it doesn't have an energy storage element. The primary voltage will not be a smooth square wave, but it still has mostly a square wave frequency. So creating this delta phase shift, you can transfer the power and eventually charge the EV battery accordingly. So there are some similar results where even we are changing currents, we changed the current reference from 100 amps to 40 amps, and the converter is automatically able to take care of the control. And so that's seems to be a very promising solution going forward with GaN devices. So coming to the summary, basically we touched upon some aspects of single-ended DC-DC converters, and then we discuss the most important double-ended topologies. So basically, I wanted to provide an overview of which converters are actually used in practice. So I hope I gave you a quick summary, and hopefully you can actually go through some of the literature in these spaces and come up with unique designs suitable for your own application. Overall, EV charging is a very critical technology. People have been able to achieve much higher efficiencies and high power densities. And isolated DC-DC converters play a very important role in maintaining the overall system performance, and their design is extremely challenging, but it provides a lot of opportunities for innovation as well. So they provide voltage transformation. You can control the charging mode, and when you have a vehicle to grid application, these isolated DC-DC converters will also need to supply power back to the input grid. So basically that's another. So the matrix converter can be very handy because that's a bidirectional converter. So we also discussed about the full bridge and resonant topologies, some of the most important ones. I may have missed another hundreds of other topologies which are not that popular. But then there are these current fed topologies which we didn't discuss, but they are being used in some applications. But again, within our time frame, I couldn't cover all these. So overall, for regular as well as fast charging, isolated DC-DC converters can be of pretty good use. And hopefully, some of you at least will be looking at new ways of designing and improving the system with very real life scenarios of the charging modes and the difficulties that we discuss so far. So with that, I conclude my presentation. I'll be happy to take any questions if you may have.
So, dear participants, we had really very good session from Dr. Harish Krishnamurthy sir. So now it's a time for interaction. I request all the participants to feel free to contact him. So you have seen the live presentation, what he has made at University of Houston, and he shown the related publications also. So please, we can have the interaction.
Yep.
Sir, good morning, sir. Is it audible, sir?
Yes.
Sir, in LC circuit, you told that below resonant frequency, the capacity below resonant frequency and above higher resonant frequency, the
Yep.
ZVS and ZVS will come into picture. So what
Right.
happens during resonant frequency?
So at resonance, basically, so that's actually a very good question. So recently, a company called Vicor, I mean, not recently, actually, it has been a few years now. A company called Vicor came up with something called a sine amplitude converter. So what that sine amplitude converter does, it tries to operate at resonance every single time. So the good thing with such a converter application is you try to achieve soft switching at all scenarios, right? The trouble there is, in these applications, as I mentioned, we need to change the gain dynamically, right? Your battery system will have a certain voltage at a particular time, and let's say, like, EV chargers, EV battery voltages can change from, let's say, I mean, like, again, there are different types of applications, whether you use a boost converter on the secondary or not. So battery voltage can be 300 to 350 volt, for example, right? So they can change significantly. So at 300 volt, your duty cycle needs to be a certain number, or the frequency has to be a certain value if it is a LLC resonant converter. And then at 350 volt, that will be a different value. So such a scheme for a sine amplitude converter is not suitable for this type of an application, and we cannot really keep our circuit always at resonance. So it will have to, because if we need that flexibility, the converter has to operate sometimes at sometimes above, sometimes below. So the way that we try to design it maybe above, like if it's a phase shifted full bridge, we try to design it above resonance. So as I mentioned, we can actually make use of the soft switching both at turn on and turn off. I hope that answers your question.
Thank you, sir.
Yep.
I think in the chat box there is a question by Mrs. Sija. In order to avoid ringing in zero voltage switching PSFB, we need to connect additional clamping circuit.
Yes.
Will it increase the size of the system? Any drawbacks in including the clamping circuits?
Good question. So, of course, size. So this ringing actually just needs a relatively tiny, relatively smaller diodes. So the size doesn't get much impacted. So we won't, because especially like with the transformer, the remaining system itself is large. So this addition is not really a big problem. The problem, however, is the loss. So if we have this particular ringing, if you don't design it well, you may very well have a lot of losses in your diodes, and also even on the RCD snubber. So that is probably a bigger challenge. You may very well get hit by one or a couple of percentage efficiency, right? Like that's a big number. As I mentioned, we are looking at 98, 99, or 98.5% efficiency for DC-DC converters. And then the moment we start compromising on just this RCD snubber, what we are trying to do is to use maybe a higher voltage rated GaN FETs. So the GaN FETs are anyway small. So if we can afford the cost and for the GaN FETs alone, then basically we can simply avoid putting any of these number. I hope that answers your question.
Yeah, thank you, sir. I have one question.
Yes.
Usually in DAB, we have a DC input and DC output. In between, we have a high frequency AC.
Yes.
So, especially in LLC converter, we are achieving a sine wave, whereas in DAB, we are operating with a square wave. So, is there any significant advantage in
having sine wave on the efficiency of the converter?
Actually, you have brought up a very important aspect, but I didn't bring dual active bridge into this talk again because dual active bridge there are actually dual active bridge can be a decent topology, but let me try to highlight the difference. So it's a very interesting prospect. Like if you look at purely the converters, we may think that the converters are they look similar. Oh, they have 4 switches on the primary, maybe 4 switches on the secondary. But the way that phase shifted full bridge or LC or LLC resonant converter works or a dual active bridge works are all different. I mean, I hope we have time, so maybe I'll spend maybe a couple of minutes in charting out the difference because these are very important. So the phase shifted full bridge, you can envision like you want to keep the transformer leakage inductance as small as possible. So what you're doing is basically applying a certain voltage on the primary side, and you are expecting that that entire thing translates to the secondary, and through either the diodes or FETs, you can take that to the secondary side, whether it is batteries or anything. So the way that we control the duty cycle, that tiny change in the duty cycle will create enough variation at the output to change the current based on what we need. So of course we need a current control on the secondary also, and I mean basically on the secondary, and so that's the phase shifted full bridge. Now LC or LLC resonant converter is, though your converters may look the same, your transformer and then the components nearby, they have LC or LLC or LCC type of networks. So what we are doing there is creating sinusoidal voltages and sinusoidal currents, which can be efficiently kind of traced to the secondary. So I will actually come to the benefits of and the disadvantages of sine wave in a bit, like after I talk about the dual active bridge. So with this, actually, the main advantage actually is you want to keep your sine wave ends, because the sine wave has a zero crossing, and then you want to keep the sine waves ends, like especially whether positive half cycle or negative half cycle, very close to the transitions of the switches. So when the switches turn on and off, your current is either zero or close to zero. So that provides you much more benefits in terms of the switching loss, because the switching loss will be low. But the challenge there is your peak of the sine wave is higher than the square wave, which in a phase shifted full bridge. So your conduction loss, if you don't take care of it properly, it can go high. So that's why, like, if you're going with a resonant converter, you would want to make use of it by trying to go with a very high switching frequency and then very fast, very small transformer size. So the applications where for you the size is very important. Then LC or LLC or LCC type of resonant converters will be very good. And these two which I mentioned, they are more or less, these two topologies will work even when you have a single input source and you have either a resistive load or a battery load or any of those loads. These should work. But for a dual active bridge, preferably, or like to make it work effectively, you would need dual active bridge. Basically, you need to have two active sources. And I do agree, EV is a very good example of that. So the main difference in a dual active bridge is you must have, I worked when I was at Google. I worked at like physically building a dual active bridge. So you need to have large enough series inductance in series with the transformer. So what this does is, some people say that, oh, you try to increase the leakage inductance of the transformer, but that will lead to a completely unoptimized transformer design. So the best practice for a dual active bridge is to have an external inductor in series with the transformer, because that acts as a power transfer reactor. So what it does is you have two sources. You create, you use two converters on either sides to create an AC waveform across the transformer inductor duo, and you appropriately create a phase shift or some variations in the angle to transfer the power that is required. So the transfer of power works very similar to that in a power system. When you have two AC sources and you have an inductor, and how do you transfer power? So these three, though they look very similar, their operating mode of is very different. So dual active bridge, in that case, it has some challenges, because if you choose the series inductance to be a high value, it is possible that you may not be able to transfer the full power. So now coming to again like the sinusoidal waveform. So like I said, it's mainly done to create that resonance and then lead to a zero crossing when the magnitude is low. So you can reduce the switching loss. That's the main benefit of sinusoidal. Hope again it's a long answer for your question.
Yeah, it's a really very good answer, sir. Thank you. I think we have another couple of questions in the chat box. I think another question: in high frequency like 85 kilohertz, what type of switches and drivers are mostly used for high power chargers?
Pretty good. So 85, I can say that many companies, including Tesla, I think they are using silicon carbide FETs. So, and not even 85, more than 300 kilohertz. So you can imagine. So the technology, this is what like we keep getting surprised by industries. Like I see that several industries are way ahead in several technologies, of course, compared to universities. So, especially on the EV charging front, I think companies like Tesla are really a leap ahead in compared to many other places. So I think I'm assuming they will probably be using anywhere from 300 to 500 kilohertz, and such applications for what is typically done is I talked about this AC level 2 charging, right? So up to a 20 kilowatts, they may design one converter. And then for fast charging, they may simply use 4 of them in parallel. So we didn't discuss that aspect. So the interleaving of isolated DC-DC converters. So it is very much possible that this way actually you can simply use the same converter, same optimized thing. It's just that for a higher power, you simply parallel connect them and interleave them. So when you interleave, your filter sizes can be reduced. And also you don't really have to create a much larger converter, a single converter, whereas here you have that flexibility as well. So typically, like you can imagine, anywhere from less than 20 kilowatts, 300 to 400 kilohertz transformer frequency, where ferrite or a nanocrystalline core for the transformer can be very handy. And using silicon carbide FETs, you should be able to achieve these rating pretty easily.
Participant had a clear idea. So one more last question. Let us take this as a last question. How to select KQM value of LLC resonant converter?
Okay, that's again. So again, if you look at our paper, you'll probably get a better idea. But it is indeed a little challenging. See, if we increase the, as I mentioned, right? If we increase the K value, which is what naturally a transformer will do, right? Like let's say if you have a transformer, you may have your magnetizing inductance maybe 500 for a high frequency transformer, maybe somewhere around 500 microhenry, and then your leakage inductance will be about 1 or 2 microhenry, right? Like, which means K is very high. So if you need to reduce the value of K just by natural design process, it is a bit challenging. So what we found out is that in order to increase the value of K, as I mentioned, like playing around with the transformer is not a good idea, especially with leakage inductances. You would make your transformer relatively less optimal. So try to design the best transformer possible, and then always add maybe a series inductance. But when we do that, then there is some additional core loss in that inductance, or some losses because you're operating at several hundreds of kilohertz. So that's a big challenge. Now increasing Q, that's again a very big challenge, right? Like you need to use certain unique types of wires, and then use the smallest, if somehow try to reduce the proximity, proximity effects, and try to reduce the winding resistances and things like that. So so the design, like to increase the value of Q, it is again a challenge. You may have to go with Litz wire or hollow conductors, depending on whether you're doing a wireless charging application. So this all these will need to be done as a multi-objective optimization function. The best thing to do will be to, for your specific design, come up with design equations as I showed you in the slides. You can again, like I said, look at our paper, take those equations, and then use MATLAB or some function to come up with an objective function and optimize the overall like effect. Like you consider all these different scenarios and then come up with a trade-off. I think that's probably going to be the best way forward. Hope that answers your question.
So thank you very much, sir. I think in the chat box, we have received very good feedback. So extremely, we are very happy and delighted to have you in the morning presentation.
Yeah,
so one participant mentioned that he has attended third time your session, but he is find very, very interested. So hope that the high gain, especially isolated DC-DC converter, is one of the cutting edge technology. As you mentioned, there are plenty of advancement is going on. I hope you have spent more than 10 years on this title. You may be a real master to talk each and every corner of this isolated DC-DC converter. So thank you very much, Hari sir, for your excellent research as well as showing the presentation. On behalf of all the participants and on behalf of the FDP and my own behalf, I express my sincere thanks to Dr. Harish Krishnamurthy, University of Houston, for his wonderful session. So once again, I really appreciate his timely effort, especially you know that in India now we are facing 11 o'clock. I think he is midnight now, closer to midnight. So without minding the timing, he readily accepted the invitation, and I really worried how he is going to deliver the lecture. I thought of making night at India and making him comfortable, but he reversed. No problem. I alone will come in the night, and you can be in coming day. So we have to really salute his effort and support. Thank you, Hari sir. Once again, I thank really on behalf of all the participants for your patient at especially closer to midnight and sparing your valuable time. Thank you, sir.